Yes, so thanks for inviting me. It's great to be here. So let me start by motivating this talk. It doesn't go forward. Okay. Oh, good. Thank you. Okay, so this is the first paragraph from the ICM proceedings written by Paul Seidel, titled Fukaya Categories and Deformations. So he says that after they made their first appearance, so Fukaya is the one who kind of invented these categories, and it was brought to the attention of a wider audience through the homological mirror conjecture of Kontsevich. Since then, Fukaya and his collaborators have undertaken the vast project of laying down the foundations. And as a result, a fully general definition is available. The task that symplectic geometers are now facing is to make these categories into an effective tool, which in particular means developing more ways of doing computations in and with them. So, Kontsevich's one conjecture is that the Hochschild cohomology of a Fukaya category is the same as the quantum cohomology of the manifold. So this is my motivation to study this subject. And one more word. So the generators of Fukaya category are Lagrangian submanifolds, and the morphisms are given by using, are defined using some Lagrangian intersection Floer theory. But in today's talk, I am not going to go into the full generality of Fukaya categories. I just focus on single Lagrangians, in which case what we have is a Fukaya algebra and its Floer cohomology. And I will be telling you what these concepts are. Okay. So what's so basically it's like a lot of heavy machinery is involved in this subject, and I'm starting from the basics. So at times the talk might be just somewhat impressionistic. Okay, so a Lagrangian submanifold in a symplectic manifold is a half-dimensional submanifold on which the symplectic form vanishes. Okay, and the most kind of famous, or rather the first example one sees of a Lagrangian submanifold is the zero section of a cotangent bundle. But we won't be seeing that Lagrangian in today's talk a whole lot, because our manifolds our symplectic manifolds are going to be compact. Okay. Yes. And Floer homology is an invariant of a Lagrangian, and it's computed using counts of holomorphic disks in X whose boundary lies on L. And the counts of disks can be given an algebraic structure, which is called an A-infinity algebra. So in the next maybe couple of slides, I try to tell you what an A-infinity algebra is. So an infinity algebra is a graded vector space along with a family of maps. So each of these maps takes D inputs and spits out an output. So 2 minus D is just a shift in grading. So you may note that for now, but it's really something that takes in D inputs and gives an output. And these family of maps satisfies this relation, which I now explain through a picture. So what's going on is your mu D is something that takes in D inputs, gives an output. And you look at the number of ways in which this block can be broken up into 2 blocks, okay? So those indices there, so this is N, that is M, so this is mu M, M, this is D minus N minus M, and this is mu d minus m. Okay, so for different values of n and m, this gives a way of breaking up this one box into two boxes. And if you were to count all these boxes and add them up, you get the right-hand side of the relation. So and we want that sum to be 0. Okay, now now I go back to the symplectic manifold. So what we have here is on a symplectic manifold, in order to define holomorphic disks, I need an almost complex structure. So I choose an omega tame almost complex structure. So tameness essentially means that for any non-zero vector, I have a positivity condition. And I consider holomorphic disks. So these are maps from a disk. So view a disk as a unit disk of the complex plane. So it has a complex structure on it. And you consider maps to X such that the boundary maps to the Lagrangian submanifold. And it is holomorphic with respect to J. So this is the holomorphicity condition written over there. So it's just complex linear. The derivative is complex linear. Okay, so and we count maps with homological constraints on the boundary. So if you were to just count these, you'll get all kinds of dimensions in the moduli space. And in order, so as you may have seen in Gromov-Witten theory, in order to get these zero-dimensional moduli spaces which you can count, you need to put some homological constraints on marked points. So we do something similar here. So, except that these homological constraints are on the boundary. So we consider cohomology classes on L, the Lagrangian, and take cycles, those that are, sorry, there's a typo here, there should be Li. So you consider cycles that are Poincare duals to these Li's, and you define a moduli space of disks. So these are disks which have marked points, n marked points on the boundary, and you require that these marked points map to these cycles which are the Poincare duals of your input cohomology classes. So this is like pretty standard stuff in Gromov-Witten theory. The only difference is that when you're working in Lagrangian Floer theory, you need to put these, do all this on the boundary instead of just in the interior. Okay, and you need to mod out by reparameterizations of the domain, which is the disk, and in so that's a three-dimensional group that you get. Any questions? Yes. So exactly. So this moduli space is the input for it is these cohomology classes, and you need to pick cycles which represent that cohomology classes. Yeah. Yes. So I am kind of throwing in everything. Yes. Yeah. So, but later when I say that I want, I'll come there in a second. Yes. So it's right there. That's there in the first line. So when you require, for certain homotopy classes of disks, the moduli spaces will be zero-dimensional. So for any L you pick, you get contributions from a certain bunch of homotopy classes. Okay, so these contribute to the Floer theory counts. And what we are going to do is we are going to represent these cohomology classes by Morse cocycles. So I avoid this difficulty of picking the right Poincare dual and all that, and instead I can just deal with Morse functions. So in the next couple of slides, I go into a digression and explain what is Morse cohomology. But if you have seen this before, this won't take much time. If you have not seen this before, this is useful because a very similar concept applies in Floer theory. Yes, Ritvik? Yes, yes. Yeah, so if you've seen Morse theory, you'll be bored for 5 minutes. Okay, so what is, in order to define Morse cohomology of a manifold, you choose an auxiliary data, which is a smooth function with non-degenerate critical points and a generic metric. And the index of a critical point is the dimension of its stable submanifold. So let me straight away put down an example here. So let me take M to be S2, and let me draw S2 in a funny way. This is my S2, and F to be the height function. So the height function has 4 critical points. And the indices are, so if it's a maximum point, the stable manifold is just 0-dimensional. So, so stable manifold means it's a set of points which are flowing to the critical point under the gradient flow, downward gradient flow of F. Okay, so for A and C, which are maximum points, the index is 0. So B is a saddle point, so it has index 1, and for the minimum, an open set of the manifold is going to be the stable locus, so the index is 2. And then the Morse cocycle is, so the jth Morse cocycle is generated by critical points of index j, and the co-boundary operator is defined by counting isolated flow lines. So you will get, so by flow lines I mean gradient flow lines, downward gradient flow lines of F. Okay, so so you will get isolated flow lines only if the indices of the endpoints differ by 1. So in this case, from A to B, you get an isolated flow line. Let me use pink for the flow line. So this is an isolated flow line, this is an isolated flow line. So these are the isolated flow lines, and using these, I define the co-boundary operator as if the flow line is going from P to Q, then that it would contribute with some sign to the co-boundary operator of P. Okay. So MPQ is the moduli space of gradient flow lines from P to Q, and the dimension of this moduli space is given by the difference of indices. So this will be 0 only if the indices differ by 1. And one can show that, so this is what I wanted to emphasize. In order to show that the boundary squares to 0, you need to look at one-dimensional moduli spaces of flow lines, and the endpoints are broken flow lines. So, so the moduli space of, say, flow lines from A to D is going to be one-dimensional. And if you look at the boundary of this, so it's going to be all of these. So it's a one-dimensional moduli space. So so the boundary of this is 2 broken flow lines going from A to B to D. So this is one, and the back one is another. So you have 2 broken flow lines, which are the endpoints. And if you count all these endpoints with sign, they should add up to 0 because they are endpoints of line segments. So that's why you get the boundary squares to 0. How do I define the moduli space? So one way to define the moduli space is just look at all, if you are going from P to Q, look at all points whose backward flow goes to P and forward flow goes to Q, and then you mod out by translation along the flow line. So that's one way to define. So in order to get this moduli space to be a manifold, you need a generic metric. Yeah. Yes, so I'm doing cohomology. If I were to do homology, it would be the other way around. So it's just a matter of, you can just flip the whole thing. Yes, exactly, yeah. Okay, so since you have boundary squares to 0, you can define cohomology as kernel mod image. And my Morse cocycles, which I'm going to use in the definition of Floer cohomology, these are just unstable manifolds of critical points. Okay, so now back to Floer theory. So now, since I have to, I'm using cocycles which are coming from Morse theory, and also because this way of defining Floer theory it's really nice. So here, instead of just looking at taking your domains as disks, you kind of put more stuff into the domain. The domain of these, instead of these treed holomorphic disks are called tree disks. So this consists of a surface part, which is a disk, and a tree part, which are going to be just infinite line segments, sorry, semi-infinite line segments. So a tree disk looks like this. It has a surface part and a tree part, which is a semi-infinite line segment. Some inputs and a single output. So this is what a tree disk looks like. And I consider maps from tree disks. So this is the tree part into x comma L. Let's call this map U. So on the surface part, it's a holomorphic map. And on the tree part, gradient flow lines on L. So all of the part in blue, the boundary and everything attached to the boundary maps to L. And the inside maps to anywhere in X. Okay. So the tree part basically maps to gradient flow lines. Where is it written? The tree part is mapped to gradient flow lines on L. So we made a choice of a Morse function here. And the moduli spaces which we are going to consider is, earlier we fixed these cohomology classes, and now fixing cohomology classes essentially amounts to fixing some formal sum of critical points. So let me just work with critical points. So what I demand is that this is asymptotic to critical point L1, this is L2 and Ln, and the output is asymptotic to a critical point L0. So L0 to Ln are critical points, and so given a set of critical points, we define the moduli space to be of treed holomorphic disks with gradient segments asymptotic to those given critical points. So this is the picture to keep in mind. Okay, and now how do I define the A infinity algebra? 1 minute. So recall that an A infinity algebra consists of a graded vector space and these composition maps, so n-ary composition maps for all n. So that's the data I'm required to give you. So the graded vector space, I say, is just generated by the critical points, and the grading comes from the indices. And the coefficient ring I'm going to use is called the Novikov ring. So this is just Q is just a formal variable, and I consider polynomials infinite polynomials in Q. So the only requirement is that as Ci goes to infinity, Ci goes to infinity as I goes to infinity. So if you put a bound on the exponent of Q, you get only finite number of terms. So that's the only constraint on a Novikov ring. And Q is a formal variable. Okay, so that's my graded vector space. And the A infinity maps are defined using these moduli spaces, which I described as in the previous slide. And how I describe it is if L1 through Ln, so recall that L1 to Ln are critical points of the Morse function on the Lagrangian. And so I just count the zero-dimensional component of those moduli spaces and see what all occurs in the output. So some critical point would occur on the output. That's a mistake again. So this is not A naught, this is L naught. Yeah, I changed my symbol at some point, and obviously I didn't change it everywhere. So this is indeed an element of the CFL. Any questions about this? Okay. So let me skip this point. So this point 3 explains what this quantity rho u is, but let's skip that for now. It just, rho u is just some element in the Novikov ring. But let me go to point 4, where I try to say why the A infinity relations are satisfied by these maps, which I've just described. So, so why are the A infinity relations satisfied? So the important thing here is that when you are looking at holomorphic disks, so just if you were looking at holomorphic spheres, you know that a sequence of holomorphic spheres can converge to a reducible limit, right? As in algebraic geometry, you see this. So a similar phenomenon, so in symplectic geometry, I call that sphere bubbling, because you get an additional component which we think of as a bubble, and it's a sphere bubble, at least in genus 0 case. So, but in the case of a disk, you can get a disk bubble. And this disk bubbling is a codimension 1 phenomenon. So let me say what that means. So it means that suppose I have certain configurations, okay? U is of a certain homotopy type, so that this moduli space has dimension 1. Then these kinds of configurations, sorry, let me draw it some other way. So these kinds of configurations where these two homology classes add up to this relative homology class, L1 and say L2 goes here, this is L3. So this type of configuration is going to have dimension 0. So you'd have a line segment of these configurations, and the endpoint is going to look something like this. But in the treed holomorphic setting, I allow more phenomenon to happen. I allow, in place of nodes, just like in place of nodes, gradient segments to develop. So these are also allowed configurations in the treed holomorphic world. This is L2. And so once this kind of a node develops, you may put in a tree component here, which is a gradient line segment, and these kinds of configurations will be dimension 1. And in the end, we have the breaking of the Morse trajectory, and then you end up getting something like this. And so this is dimension 0. So in the Morse case, we saw that the breaking is a codimension 1 phenomenon. So what happens is, if you consider a one-dimensional moduli space as its endpoint, it will have this kind of a configuration. And if you count all such codimension 1 configurations for a one-dimensional moduli space, you precisely end up getting the A infinity relation. So in this case, for example, this one, for example, is what? It is mu2 of mu1 L1 comma L2. So this is the number of ways of splitting up a 2-input box. So, and if you consider all possible cases, those will occur as endpoints of this moduli space. So you'll have various components. So if you count them with sign, you precisely get the A infinity relationship. Yes. 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 Yeah, that's a good point. I mean real codimension 1. Exactly, you cannot integrate, yes. Yeah, that's why you get these more complicated structures. Yeah, and then some observations about this structures I've just described. So what is, there's also a mu0, that's something which takes no input at all and just spits out an output. So that's just a disk. So it's just a count of disks with one output and no input. Therefore, it has no terms with a 0th power of q. So otherwise, you can also have a 0th power of q. For example, in the mu1 case, from P2, if you are at a critical point, you could just have a gradient flow line with no disk. So if it's an isolated gradient flow line, that makes an appearance in mu1. But in mu0, you have no such contributions. So really speaking, so the data of Morse theory is completely embedded into the A infinity algebra of a Lagrangian. So if you just set q equals 0, what you recover is the A infinity algebra associated to Morse theory. Okay, so in order to define Floer cohomology, we need to assume that mu1 squares to 0, because once you have that, you can define your cohomology as the kernel of mu1 mod image of mu1. But this is not always satisfied because of the first A infinity relation. So if one were to draw the first A infinity relation, so what is that relation? It is a disk A So these kinds of contributions add up to give 0. That's the first A infinity relationship. So this is your mu1. This is a mu1 contribution. But a mu1 followed by mu1 does not square to 0 because you also have these disk bubbles like this one here and that one there. Okay. So this is, this next point is, some algebraic nonsense at this point, but when you start doing the geometry, it becomes meaningful. So what is it? It says that if one of the ways you can define Floer cohomology is it gives you, so I'm just trying to give you a condition where the Floer cohomology can be defined. So, we say that an A infinity algebra has a unit if there is an element EA which satisfies this condition. So if you plug it in any mu n other than 2, it will give a 0. And if you plug it into mu 2, it gives the other element. So if there is this kind of an element, then, and your mu 0 is just a multiple of the unit, then the A infinity algebra is unobstructed. And if it is unobstructed, what happens is if you go back to the first A infinity relation, the bad terms, that is the first and the second term, they vanish, and you're just left with mu 1 squares to 0. So if for an unobstructed A infinity algebra, one can define Floer cohomology, and in such a situation, if the Floer cohomology is non-trivial, then that's when we say that a Lagrangian has non-trivial Floer cohomology. Sorry, this is technical. It cannot be helped, but from after this, I get to some examples to give a sense of what these Lagrangians are geometrically. Okay, so so what does it mean geometrically? Like, can we see this Floer non-triviality in simple terms, other than them making their occurrence in like Fukaya categories and mirror symmetry? So if you were to just look at manifolds and spaces, one of the geometric consequences of Floer non-triviality is that if a Lagrangian is Floer non-trivial, then it is non-displaceable. Okay, and non-displaceability is defined as follows. It's that if for any Hamiltonian diffeomorphism, if the image of the Lagrangian continues to intersect the Lagrangian itself, then the Lagrangian is called non-displaceable. So I start by looking at the really simple case of S2. So S2 has a symplectic form, is the area form, and and the Lagrangians are any one-dimensional submanifold is a Lagrangian, right? Because omega is a two form, so it will vanish on any one manifold. And the question is, are there any non-displaceable loops in S2? So if someone has not seen the definition of a Hamiltonian diffeomorphism, in the two-dimensional case, you can just, rather in the S2 case, Hamiltonian diffeomorphism is just an area-preserving diffeomorphism. So for which loops is there no area-preserving diffeomorphism which displaces the loop? And the answer is a loop that divides S2 into halves of equal area, because any area-preserving diffeomorphism will continue to preserve this property of the loop, and therefore the two loops will have to intersect. So we have found a non-displaceable Lagrangian in S2. Okay, and if you try to compute the Floer cohomology, you will actually get that the Floer cohomology of the loop in S2 is non-trivial. So it is unobstructed and Floer non-trivial. Okay, and so these were the initial motivations for developing this theory by Floer. Floer wanted to give a lower bound for the number of intersection points of L and the image of L under a Hamiltonian diffeomorphism, and that's why he developed Floer theory. But now it's much more than that, and it's defined in much more generality than Floer initially thought of. So in Floer's definition, there were no disks. He assumed that pi2 of x comma L is 0, but now the disks are like a major contributor to our story. Okay, so now I move our discussion to toric symplectic manifolds, because here we have lots of Lagrangian manifolds to play around with. Okay. So what is a toric symplectic manifold. So I'm not giving the full definition. I'm just trying to give you a sense of what it is so that we can, I can talk about the Lagrangians there. So basically a toric symplectic manifold is just a smooth toric variety. If you were to look at it purely in the symplectic geometric world, it's a symplectic manifold with a Hamiltonian action of a half-dimensional torus, and this action is generated by something called a moment map. And the image of the moment map, which is called the moment polytope, is convex. So let's look at a couple of examples. So the simplest example is the S1 action on P1. So maybe this is something I wrote in the next slide, but let me tell you this now itself. The reason I'm looking at these is because the fibers of the moment map are Lagrangian submanifolds. So one can almost think of your symplectic manifold as being a fibration over a convex polytope whose fibers are Lagrangian tori. Okay, so let's do the examples and we'll see better. So in case of the P1 S1 action on P1, the moment map is the moment polytope is just a line segment. Exactly. So this is for the interior points in the polytope. So in this case, the picture is as follows. P1 is just a sphere, and it has two fixed points of the S1 action, and all the other orbits are mapped to interior points in the line segment. So this is the, say, 1, 0, and 0, 1. So except for the endpoints, above all the points, we have a circle as fiber, which is a Lagrangian in P1. Okay. The next example is a very silly extension of this example. I just take the product. I take the product of the group, and I take the product of P1. And as you would expect, the moment polytope is also a product. And all the interior points are two tori. So each of them is an orbit of the group action. And the fixed points go to the vertices. And over these points on the one edges, the fibers are circles. So in the interior, all the fibers are two tori. And that continues to be the case in my next example. Is P2, whose moment polytope is a triangle. And this, for example, is the divisor Z1 equals 0. So I just say this later, that the vertices correspond to fixed points of the torus action, and one-dimensional edges are torus invariant spheres. So above every point, you have a circle as a fiber, and facets meaning codimension 1 boundaries of the moment polytope, they correspond to torus invariant divisors. So in the P2 case, you have 3 torus invariant divisors which go to these 3 sides of the triangle. Okay. Yeah, and similarly, we can do Pn, and in Pn, you have n+1 toric divisors, and the moment polytope of this is just an n an n, whatever it's called, an n simplex maybe. I was teaching algebraic geometry. Simplex is what is in my mind. So P3, for example, is a tetrahedron. Let me just do P3. Okay, so the moment polytope of the S1n action on Pn is given by that polytope there. N plus 1 vertices and some polytope spanned by that. And the fibers of the interior points are Lagrangian tori, and this I already said. Okay, so I move on. Okay, so then more interesting examples. Yes. So for one, there's a lot of things. So for one, I was able to just write down the infinity relations much more easily because they break up in a nice way. And also, in order to define these, I need to do perturbations of the almost complex structures. And you need to say this. Yeah, maybe we should talk about this. You can reserve this question for the end of the talk because it doesn't. Yeah, so remember to. This can be a question. Okay, so a blow up. Yes, so how blow up in, if you want to blow up a point in a symplectic manifold, the way one does it is you delete a ball around that point of radius epsilon, where epsilon is some small constant. So this is a Darboux ball centered at P, and then if you, after removing this ball, you're left with an S2n minus 1 boundary, and you quotient that boundary by the S1 action, and that's the blow up. Okay, so you can think of epsilon, the way epsilon manifests itself is that the symplectic form on the blow up is of class omega, like the pullback of omega minus epsilon times the exceptional divisor produced by the blow up. So yeah, in an algebraic setting, you don't see this epsilon because you're not talking about what is the form on the manifold, but since you have to keep track of form, you have to keep track of what's called this blow up parameter. Okay, so in case of CP2, if you do a toric blow up in general, what happens is that deleting this ball corresponds to chopping off a tiny piece of the moment polytope. Okay, so if you do an epsilon blow up of a point in P2, and in particular, let me take my point to be 0, 0, 1. I have to take this to be a toric fixed point. Otherwise, it's not a toric blow up. And the moment polytope for this guy is, you start with the moment polytope of P2 and chop off an epsilon triangle there. So that's the moment polytope. Okay, and so these are my examples of toric symplectic manifolds. And the big result of Fukaya and his collaborators is that they were able to kind of characterize all the Floer non-trivial tori in toric submanifold. So in a toric submanifold, we have all the interior points. Every interior point corresponds to a Lagrangian tori, and their theorem tells us which of these Lagrangian tori have non-trivial Floer homology. So I'm not even stating this theorem correctly. So I'm trying to say it in terms of quantities which we have already encountered, but in the process just making a wrong statement. So roughly speaking, what it says is that the mu naught term, which was a count of disks, is now a function of lambda. So lambda is tells you which Lagrangian it is. So the lambda Lagrangian, if you're looking at the lambda Lagrangian fiber, and you look at the mu naught in its A infinity algebra, as a function of lambda, this should have a critical point. Okay, so geometrically, what this roughly means is that you get these critical points when the disks, so remember that mu naught is a count of disks. So when these disks balance each other. So I'll give you a few examples to make it clear what I'm saying. So before that, what I want to say is that in toric manifolds, these disks are very well behaved because toric manifolds are GIT quotients of Cn. So disks in x, L are just going to be Blaschke products. And in nice cases, the leading order terms in mu0 come from disks with a single intersection with one of the toric devices. So let me move on to the examples here. So in the P1 case, we said that the equator is a Floer non-trivial Lagrangian. And the disks it bounds are two disks of equal area. So in some sense, these two disks are balancing each other. And in the P1 cross P1 case, that's similar. You have these four disks which are balancing each other. Maybe let me draw disks with pink. So this is a disk and this is a disk. And note that the reason I'm drawing the disk this way is each of these disks has its boundary in the Lagrangian, and it has a single intersection with one of the toric divisors. So this means that this has this intersection with this toric divisor. So if you were to, sorry, maybe I should have said this here. Sorry. When I say toric manifolds are GIT quotients of Cn, this n is the number of facets. So Cp2, for example, it is the GIT quotient of C3 by C star. So it has 3 facets. So vanishing of one of the coordinates is same as the disk intersecting that divisor. Okay, so where am I? So the next example is P2, where the Lagrangian tori with non-trivial Floer cohomology has coordinates 1/3, 1/3, and it has these 3 disks of equal area. And similarly in Pn, we'll have n plus 1 disk. So let me draw the P3 case. So here there will be 4 disks. Okay, so now let's do the blow-up case. So the blow-up case is really interesting because what happens with Floer non-trivial Lagrangians, it depends on the size of the blow-up. So if your blow-up is small, then what happens is you continue to have this Lagrangian, which is the Clifford torus. So sorry, I maybe didn't mention it in the previous slide. So these Lagrangians in the Pn, I call those Clifford torus. So you continue to have the Clifford torus, but near the exceptional divisor, you get a new Floer non-trivial Lagrangian. Let me call this L1, and it is balanced by these 3 disks. Okay. But if you do a big blow-up, which means that big epsilon, then the picture becomes something like this. So there it is more helpful to think of this as a P1 bundle over P1, so which is the Hirzebruch surface. But in the general case, if you were on Pn, that's what I wrote here, it's a P1 bundle over Pn minus 1. And the fibers are small. By small, I mean the symplectic form on the fibers is much smaller compared to the symplectic form on the base. So the Floer non-trivial Lagrangian here is given by something in the middle. So here there is only one Floer non-trivial Lagrangian, and the disks are as follows. There is two small disks incident to those two divisors. So these are in the fiber direction, and two large disks in the base direction, which are incident to two other toric divisors. So this last thing is an instance of balancing in stages. So in all the other cases, all these disks were of equal area and they were balancing themselves. But you could also have a thing of balancing in stages where these two small ones balance each other, and then you look at the base direction and these are balanced by a big one. Okay. Right. Let me go back to I forgot to write a point. Okay, so there is this result of Charest and Woodward, which says that if you have a small point blow up, if the epsilon is small enough on any manifold, on any symplectic manifold, if for a small enough blow up, you always get a Floer non-trivial Lagrangian close to the exceptional divisor. And the balancing disks will be given as follows. So, and the idea of the proof uses like kind of splitting up the manifold into two parts, one close to the blow up and one far away. And that's done using an operation called symplectic cut in symplectic geometry. And what's a symplectic cut? So if you have a separating hypersurface, which is which has an S1, a free S1 action on it, then we define, so Z separates X into two parts, which I call X plus and X minus. So I break this, so I get a manifold with boundary Z, and I mod out Z by the S1 equivalence relation. So the resulting two spaces are symplectic manifolds. And by modding out Z, I get a codimension 2 submanifold in X plus and X minus. So this will be a symplectic divisor, but in X plus and X minus, the normal bundles are going to have opposite signs. And this cut operation can be reversed by what is called a symplectic sum. So if you were to do a cut, you can put these back via a symplectic sum operation. And this symplectic cuts interact very well with moment maps. So in particular, if Z is a hypersurface in the moment polytope. So for example, I don't want to erase, I can go there. So for example, if you have if this is your moment polytope and you take Z to be the inverse image of this hypersurface, so then the torus action descends to the cut spaces, and they are going to have those two moment polytopes. So you can literally break a moment polytope into two parts, and those would be the moment polytopes of the spaces arising out of the symplectic cut. So that's why I've written here. So if Z corresponds to a hypersurface in the moment polytope, then the moment map descends to the cut spaces X plus and X minus. Then the moment polytopes are of X plus and X minus are obtained by cutting the moment polytope of X. And another example of cut space is a blow up. So you can think of a blow up as just cutting along this hypersurface. So your blow up manifold is one of the cut spaces. And the other cut space is just going to be CP n, where n is the complex dimension of the manifold. Okay, so and the idea of this this theorem which I just mentioned of Charest and Woodward, what they do is the following. So let me restate the theorem since it didn't occur in the slides. So the theorem was that if there is a small blow up of a small point blow up, there will be a Floer non-trivial Lagrangian close to the exceptional divisor. And the way it is proved is that near a point, you can always take a Darboux neighborhood. So it will just look like, say you are on a point on CPN. Oh, my time is over. Okay. Huh? 5 minutes? Okay. Thanks. So the idea is the following. If suppose you are just on CP2, and I do a cut here, so that the disk here is to this divisor is much larger than these pink disks, then I have Floer non-triviality on this space. But then I might as well glue in any other manifold, it doesn't matter. So if locally you take a Darboux chart and the torus action and you do a symplectic cut, the rest of the manifold can just be anything. So the main idea of the proof is to claim that when you, they kind of develop a theory called a broken Fukaya algebra. So if you have a symplectic sum, the infinity algebra of a Lagrangian can be written as a combination of contributions coming from both the pieces. And if one of the pieces is toric Fano and has balanced Lagrangian with none of the disks, balancing disks incident on the separating divisor, then the Lagrangian is Floer non-trivial on all of X. So that's the kind of sense I was trying to convey. So if this is your separating divisor, but this is far away that the balancing disk, it doesn't interfere with the balancing disk, then I have Floer non-triviality on all of the manifold. So these ideas can be put together to kind of look at blow-ups of higher dimensional spaces. By now I can erase some of this. So a line, by line I mean a complex line here. So let me take a blow up of, so a line is CP1, say inside CP2. So let me take the blow up of this line on CP2 and look at the moment polytope. So if this is my line L, the blow up space is going to be, take out a neighborhood and cut it off. And instead, you get a new facet of the toric, of the moment polytope, which is the exceptional divisor. So that is the moment polytope. And in this case, we do get a Lagrangian with non-trivial Floer homology, and that is somewhere, it's close to the exceptional divisor, but it's close to the middle of the exceptional divisor. So it's somewhat like in front here. So, and the balancing here happens in stages. So you have these three disks which balance each other. And then there is these two disks incident to the top and bottom face. Okay. And in general, if the neighborhood of a line in a symplectic, a complex line in a symplectic manifold has a toric structure, then there is a Floer non-trivial Lagrangian near the exceptional divisor. The toric neighborhood can be isolated via a symplectic cut, exactly as we did in the point case. And in the toric piece, the Lagrangian is balanced in stages, just as what I did there in the CP2 case. And one can view this as a lift of the equatorial circle of the blow-up locus. So the blow-up locus was this line, and in some sense, this Lagrangian is lying above the equatorial circle. And so I had this like very wishful conjecture that if you have a symplectic submanifold with some Floer non-trivial Lagrangian, then if I blow up that submanifold, then the Lagrangian probably lifts to a Floer non-trivial Lagrangian in a small blow up. But this is like little too much because we need these toric neighborhoods and balancing this for both L and Ly, and that's just, so it doesn't quite work out. So however, it works out in like many families, but in particular, I decided to take one particular example of this M0 n bar, which can be realized as an iterated blow up of projective space. And in this case, I am able to show that corresponding to each of the blow ups, there is a Floer non-trivial Lagrangians. So yeah, so I'll stop here. We can, I'll maybe address his question now and then move on to other questions. Okay.
So thank you very much for the talk and the discussion.
So your question was, why is this read holomorphic disk better than the other co-cycles, choice of co-cycles, right? So one is that these A-infinity relations fall out very nicely, but the other thing is that when you say that this marked point has to intersect a submanifold, you have to talk about the intersection being transverse. So in this case, those things can be controlled by just perturbing Morse functions, and that works out quite neatly. So that's the short answer.
Some context, more natural thing to take P1 cross P1 several times and go model the action.
Yes, yes. He's giving you a mic.
Oh,
okay. Yeah, so his question was like, instead of thinking of M0 n bar as a blow up of projective space, you can also think of it as start with P1 cross P1 and do blow ups, and then put another P1 and do blow up. So that's
P1 plus several times and then go model the action of the SL2C.
okay.
Diagonal action of SL2C.
So this is not the Kiel's construction you're talking about. There's a construction by Sean Kiel.
It is also birational to this, but that is not exactly this one.
So the reason I chose this was because it has a very good iterative, is it recursive structure? Sorry, not a recursive structure. So
that also has nice structure. Anyway.
Okay, I will look at it. Okay, thanks.